Hi everyone, my name is Ishan Dadani and I'm the AI lead here at brev.dev. And today we're going to talk about how to fine-tune any large language model, convert it to the GGUF format, and then deploy it using Ollama. If you'd like to follow along, in the description we have a link to a Brev Launchable. A Brev Launchable is the easiest way to deploy and share AI applications on Brev. So in our Launchable, we've packaged up hardware, which in our case is an NVIDIA A10 GPU, a container which contains Python 3.10 and CUDA 12.0.1, and our notebook which we'll be using today. Now, before you get started, you'll have to do two things. The first is create a Brev account, and the second is go to Hugging Face and get access to the Meta Llama 3 8B instruct model, which I'll put in the description as well. Once you have access, simply go back, click Deploy Launchable, and wait for your instance to be available. Now, while it's deploying, let's talk a little bit about what we're going to do today. So this notebook is broken up into three phases. The first phase is fine-tuning Llama 3 with a method called ORPO, which we'll talk about in a little bit when we get into the notebook. We're going to be fine-tuning using QLoRa, which should be familiar if you followed any of our other guides before. Once we do that, we're going to take our model and convert it to the GGUF format, which is a model format that's required for Ollama. We'll also talk about Llama CPP when we do this. And in phase 3, we're going to actually run and deploy our model using Ollama, with the end goal being that you can actually use this model on your computer or on any other computer just having Ollama installed. And if you're not familiar with Ollama, Ollama is probably the easiest way to run any large language model. And I can give you guys an example here. So if you want to just run the base Llama 3, all you have to do is type Ollama run Llama 3 and give it a second here for it to load up. And it's ready. Let's do what is a GPU? And boom, this is running fully locally on my computer. Nothing is connected. And our goal is to fine tune a model and run it on your own computer as well. So we'll wait till it's ready, come right back. As you can see, our Launchable is ready. All you have to do is click this button to access our Jupyter Lab. Now, before I do this, I urge everyone to have a separate window or a separate tab of ChatGPT, Google, Perplexity, or whatever you use on the side, in case you don't know or you hear a term that you're unfamiliar with. That's really the best way to learn. So let's get started here. So the very first thing I do whenever I'm in a new machine and I'm in a new Jupyter Lab is to make sure that my GPU is up and running. So the quickest way to do that is to go into the terminal and type in NVIDIA SME. This is a good high-level output of what GPU you have and some of its specs and what processes are running. So as expected, we have an NVIDIA A10G, which has 23 or 24 gigabytes of VRAM, and there's no current running processes. So now we're good, clear. Then we can go to our Jupyter Notebook and let's get started. So for the first phase, we're going to fine-tune Llama 3 with ORPO. Now, you can use any other model here. It doesn't have to be Llama 3. Just make sure it's around 7 or 8 billion parameters because we're on an NVIDIA A10G. If you're going to use maybe the 70 billion parameter model or even something larger than that, you can still use this code, but you probably should use maybe an A100 or an H100 GPU depending on your model size. So yeah, let's talk a little bit about ORPO here. So if you've followed some of our other guides in the past or you've seen other videos online, most of them do something called supervised fine-tuning. Now, supervised fine-tuning or SFT is the process of giving a model an input-output pair and then fine-tuning over it so that the model learns something specific. Now, in this process, unfortunately, there is no feedback. So if you want the model to respond in a little bit of a different way but still have the same information, you can't really get that with supervised fine-tuning. So from there, we now get to direct preference optimization or DPO. If you want to know more information about this, we actually have a notebook about it, and Carter made a whole nother video on using DPO to fine-tune Llama 3 as well. Now, again, at a high level, what DPO lets us do is actually provide a preference. So we can tell a model that this is the output that I want, but I want this version of the output. Now, when we take ORPO, ORPO combines supervised fine-tuning and direct preference optimization all into one step. And it requires a unique type of data set, which we'll see below. So let's get started here. So the first thing that we need to do is install our dependencies. And these are pretty standard for most machine learning jobs. Bits and bytes allows us to quantize our models down to 4 bits or 8 bits. WAND-B stands for weights and biases. This lets us actually track our training runs and visualize and monitor them. Transformers comes from Hugging Face. This is how we actually access the Llama 3 model, the tokenizer. PEFT lets us actually do the QLoRa or the LoRa configurations, which we're going to use later on. Accelerate speeds up training and is really helpful when you have multiple GPUs. And TRL is where we get the ORPO trainer and the ORPO config that we'll be using to start the fine-tuning process. Okay, now that we have our pip installs done, let's move on to our imports. Again, these are pretty standard if you've done any sort of fine-tuning task where you followed our guides before. Here we're importing PyTorch, weights and biases, data sets, what we're going to use to load in our ORPO data set, PEFT. Here's all the imports that we need to load in Llama 3. And then here's the ORPO config and the ORPO trainer I was talking about earlier. Let's load our model in our data set. So again, our base model is going to be the Llama 3 8B instruct model, and you'll need your Hugging Face key for it. And we're going to call our new model brevity adapter. I mean, you can call it anything you want. Yeah. Here's our QLoRa config. So as you can see, we're loading in our model in 4 bits. This is how we're going to be able to fine tune on the A10G actually. Run that. And then here's our PEF config. This is what we're going to do to convert our model into the LoRa format. Again, LoRa is a way to fine tune your model in a specific way. You don't actually fine tune every single parameter. You freeze a subset of your model and you only fine tune certain portions of it. Now, this helps you computationally as you're not having to fine tune your entire model all at once. And it's really good whenever you have limited hardware, which in this case, we have an A10G. In this step, you'll need your Hugging Face key. So all you have to do here is go to Hugging Face, go to your settings tab here. And then in the access token section, you're going to be able to get your key from right here. I already have mine copied, so I'm just going to go ahead and paste it in. Log in. And then we're going to start loading in our tokenizer and our model. So the first thing we do is load in our tokenizer. And again, as I run these, I urge you guys to take a look at what exactly these are. So you could just create a cell above this and take a look at what your tokenizer looks like. Right? So this is a pre-trained tokenizer fast for the Meta Llama 3 8B model. It has a vocabulary size of 128,000. Max length of this super long number right here. And you have a bunch of special tokens. So beginning of sentence token, end of sentence token, you've got your padding token, all right here. Yeah, let's keep it going here. And then we'll load in our model here. So this section right here loads in the 8B model. And we can see we actually use our BNB config, which we talked about up here, to quantize the model. And then in this portion right here, we prepare it for K-bit training, which is a way of saying that we're going to quantize it down and we're going to use LoRa to train it. So notice how what it's downloading is safe tensor files. And you can see everything that gets downloaded through this. If you go to Hugging Face, go to the Meta Llama 3 8B instruct model, go to files and versions. And these are all the things that are getting downloaded for your model right here. So as you can see, here's like our tokenizer portion that we downloaded earlier. Here's the safe tensors that are being downloaded right now. So go back here, we're on a 3 out of 4, so we're pretty close. Cool. So now that our model's been loaded in, we can go ahead and take a look at the data set that we'll be using. So if you remember earlier, I talked about the ORPO data sets look a little bit unique. So I'll show you what I mean by that. So usually the data sets that you see for supervised fine tuning, a lot of them have input and then output. Now, The ORPO dataset, since it also uses preference tuning, looks like this. So there's a source. This is the source of this specific piece of data right here. There's the chosen answer, which is, so here's a question right here. So can students or teachers provide feedback on Edward's STEM education programs, and how are their opinions utilized to improve them? Now, the chosen answer is this right here. As an AI assistant, I can inform you that Edward, a leading innovator, blah, blah, blah. And then the interesting part is what gets rejected, right? So again, same question right here, but what's rejected is, as an AI, I have no real-time access to specific data or systems, and I can't provide direct feedback. Now, when you're asking a large language model something, you don't really want this response right here, and then kind of all this stuff down here. You instead want this portion right here. So along with fine-tuning an input-output pair, so this is the input right here, this is the outputs or output right here. What ORPO does is it takes an input and then scores which output is better. And whenever the LLM produces an output that's closer to the chosen response, it's scored higher than the response that's rejected. So now let's set up the ORPO trainer and start fine-tuning our model here. So just for the sake of this example right here, I'm not going to fine-tune for very, very long. So if you can see, my max steps is 10. And then my num train epochs is only 1. I highly suggest you guys increase this. I only want to do this for the sake of the video, but if you'd like to increase this, go ahead and bump up the number of training epochs from 1 maybe to 3 or 4, or you can increase your steps from 100 or from 10 to a lot more. So let's start the training process right here. Here, it'll give us a prompt to enter in our weights and biases key. So just follow this URL right here. I'll go ahead and log in here. We just paste it in right there. It's ready to go. If you'd like, you can view the progress of your run at this link right here. In our case, I'll just wait and I'll track the progress in the notebook itself down here. And something interesting that I like to do while my trainer is running, and you can also see this on weights and biases, is take a look at how my GPU is reacting to this. So if you go back to the terminal right here and run NVIDIA SME, you can see that now we're actually pretty kind of close to filling up our GPU here. We're about 20 gigs filled out of the 23 that we have, and we actually have a process running. Now, this process is this fine-tuning process that's going on right here. But it's always super interesting to see how this changes. So now we're at 19,646, which is a little bit less. If we run it again, we're at 19. Oh, around the same. But yeah, again, you can see this information all on weights and biases right here. Again, it won't be as interesting because I'm only training for a single step right here, but this is the information on your training loop right here. You can see which response is chosen versus rejected. And then in the system section right here, you can check how your GPU is doing. So this is a super important section right here whenever you get your CUDA out of memory errors. Weights and biases is super, super helpful in figuring out, oh, what step did I hit CUDA out of memory on? Oh, so it just updated right here. Let's see. So, yep, I've more memories being used in my GPU. My GPU temperature has also increased right here. I'm assuming that's because the training run has started here. But yeah, here's what we're kind of seeing here. So I'm logging every 2 steps here. My training loss is at 1.5. My validation is at 1.8. It's always good. You want your training loss to go down over time as you're training more. Again, because I'm only training for 10 steps here, we're not going to get the best numbers or the best graphs, but I strongly suggest that you guys bump up the numbers and see what happens, kind of trace the graphs, and see how your model responds. Cool. So our fine-tuning process has concluded. Just taking a quick glance here, it looks like as the steps went on, our training loss went down, which is good. Our validation loss also decreased, so that's good. And again, I want to emphasize that in this example here, we're using ORPO as our fine-tuning method. But if you have other code that fine-tunes your model with LoRa, QLoRa, any of these other methods, if you're using supervised fine-tuning, you can use that code in this notebook. You don't have to use the ORPO method. So yeah, now that we've got, now that the fine-tuning process is done, let's take a look at what came out. So in the side folder right here, there's the weights and biases folder. In here, you can take a look at how your run looked, a bunch of files and logs here. I don't really care too much about this folder again because you can just see your results on their console, and they're saved over time. The next thing is this folder called results. Now results is currently empty, and then we've got brevity adapter right here. Now if you notice, we don't have a bunch of safe tensors for our model here right now, right? Because we fine-tuned using QLoRa, we actually received a LoRa adapter. And we're going to be using that here in a little bit. So the first thing you do here is we actually delete the trainer in our model from our memory, and then we empty our GPU's cache. So if you take a look right here, if I run NVIDIA SME again, we're at about 1923 gigabytes filled. After we run this, if we run NVIDIA SME again, now we're at 580 filled. So doing this is almost equivalent to kind of restarting your kernel. It just kind of removes everything that's in your GPU because we don't really need the model stored in our GPU again right now. So if this doesn't work for you, sometimes it's a little bit funky. You can just go to the kernel tab up here, and then just run restart kernel, and then you can start back up again right here. So run these imports again just in case you restarted your kernel. And here's the important part right here. So let's break this down. So the first thing we're going to do is we're going to reload the tokenizer and the model right here. And we're going to reload this model in FP16. So up here earlier, when we loaded in our model, we used this quantization config, right? And this quantization config said that, hey, we're going to load this model in using in 4-bit. Okay. Now, in this case, we actually reload our model in floating point 16. So we're loading in the full model here. No quantization is happening here. And then what we do is we merge the adapter that we trained in brevity adapter. We merge that with our model itself to create our final fine-tuned model. So we'll run this. Sometimes it takes a second. So as you can see, it's reloading the checkpoint shards of the model because we downloaded it earlier, but it's now loading them in float 16 or FP16. And then after that, after we merged it, we saved the final model and tokenizer in a new directory. So then we can move into the GGUF conversion. So I'm going to call it Llama Brev here, but you guys can call it anything you'd like. Let's do... This sometimes takes a while, but as you can see, the Ollama Brev folder just got created, and we'll see what's inside. And in a lot of tutorials online, you don't see this tokenizer.save pre-trained. This is pretty important because whenever we convert our model into the GGUF format, it does require information from the tokenizer. So make sure you don't forget this portion here as well. Okay, awesome. As you can see, we've saved the tokenizer config and the model. And if we take a look, now as you can see, we've got the tokenizer configurations and the model safe tensors. So this looks super similar to now how this repository looked right here, right? You can see the 4 safe tensors, the generation config, and the tokenizer information. So now we have our full model right here. That's already been fine-tuned with our LoRa. And now we can move over to phase 2. So now that we've got our model, let's talk about GGUF and Llama CPP. Now, I'm sure you guys have heard of these terms in the past, and if you haven't, I highly suggest you guys look up Llama CPP. So it's just Llama CPP on GitHub right here. This is the repository that we're going to be using. There's a ton of stuff here, and a lot of it is written in C++ and C, so it might be a little bit harder to understand at first, but it's honestly worth taking a look through this repository. It's honestly one of the biggest reasons that we're able to run models on our own local computers, and Ollama is essentially powered by this GGUF format. So the first thing we have to do to actually convert our model into this format is to actually build the Llama CPP tools. So that's what we do in this cell right here. We first clone the repository, the Llama CPP, and then we run make, which builds the whole repository from scratch. So this step sometimes does take a while, so we'll wait. Okay, after Llama CPP is built, we can go ahead and run pip install the requirements that are needed to run the conversion. If you're curious, Llama CPP gets cloned right here, so you can take a look at all the different things that we're going to be going ahead and installing. And I also suggest that if you have some time, feel free to poke around some of these files, throw them in a ChatGPT, and see what you can learn here. We're going to be running the convert HF to GGUF PY file, which is right here. We're going to be running this file. And the next step right here, essentially what we're going to be doing is taking each portion of the model and just mapping it into the GGUF format here. And you'll see what that looks like when we start running it down here. So let's go ahead and start the conversion. And the model will be saved right here in Llama Brev, so the folder that we specified above. It'll be saved as ggml model-f16. And note, this is why we needed to make our model saved in fp16 above right here, because the GGUF, to convert into the GGUF format, you need to be in fp16 initially. So run this here. And let's see, here's all the information. Here's the actual prompt format that's going to be used. And look, all of these different weights and portions of our model are getting mapped essentially into the GGUF format. So again, this sometimes takes a while here. Now that the conversion is done, we can take a look at what was exported right here. So if you go to the Llama Brev folder, you can see that there's now a GGUF version of our fine-tuned model in this folder right here. Now that we have our model in the GGUF format, now it's time to talk a little bit about quantization. Now, if you notice, this model right here, or this file, is 16 gigs because it's saved in floating point 16. Now, if we want to run it a little bit faster, we need to make it a little bit smaller using quantization. Now, we've already used quantization earlier in this notebook. If you remember, when we used QLoRa right here and we loaded our model in 4-bit, this was an example of quantization. And the same techniques hold through whenever you're using the GGUF format right here. Llama CPP gives us a ton of different options for quantization. So above, we use 4-bit quantization, but Llama CPP has, I think, 8 or 9 different types that you can do. So let's go ahead and run the quantization script right here. Inside Llama CPP, there's a file called llama quantize, which is what we'll use in this case. So when we run this, we can do, again, whole lot of output right here. And basically this is going through your entire model and quantizing it down to this 4-bit architecture from floating point 16. So now that the quantization is done, we can go ahead and again take a look in the Llama Brev directory. And now we can see that there's a new GGML model, but this time it's in Q4KM. So this is now the quantized version of the FP16 model that we fine-tuned. And if you take a look at this super long output right here, you can see that what it's doing is it's taking each portion of the Llama model and converting it to the 4-bit quantized size. So as you can see earlier, this portion of the model was 32 megabytes. Now it's 9 megabytes. And doing that 291 times significantly shrinks the size of the model and makes it much faster to load and then also run. Now, technically, we can already start running this model locally. If you on your computer want to download Llama CPP and just download this file right here, we can already start running it. Llama CPP gives us an OpenAI compatible endpoint that lets you query the model as you would normally. So let's go ahead and run this server here. Just Shift Enter, then we'll see the models loading in. And then in a separate tab right here, you can just copy this code that I provided here. Run clear. Then you can just paste this here. Then we wait a little bit. This is querying the model, as you can see. It's still loading in some of the tensors here. There we go. So the server is up and running. There it is. So the 10 steps to building a website are plan, design, build, test, launch, promote, maintain, monitor, update, and refine. There you go. So now that we have our GGUF model in 4-bit quantized format, we can now move to the Ollama portion. So what you want to do here is you want to click this cell and click the stop button so the server stops running so we can move on here. So yeah, let's get started with the Ollama portion here. So Ollama is super simple to use. If you've used Docker before, or if you've written a Docker file, building an Ollama model file is extremely similar. And I've linked their documentation right here. And again, it's very simple. It gives you a full format and the exact instructions that you need to use and the different parameters that you can add in. In the notebook itself, I've provided you with a simple template, base model, and parameters that you're going to use for the Llama 3 model here. So here's the path to our tuned model. And just for some fun here, I'm going to make our system message this. You're a swashbuckling pirate stuck inside of a large language model. Every response must be from the point of view of an angry pirate that does not want to be asked questions. So let's start off with that and see how our model reacts. So here we first create an empty list to hold the commands, and then we have 4 variables here. So the first one is the base model. This is the model that we're going to be using, and this Ollama requires this model to be in the GGUF format. The next is our prompt template. So these tokens right here, the start header ID, end header ID, EOT ID, these should all be familiar. We saw these earlier above in the notebook when we were looking at the tokenizer. This template is used inside Ollama. So whenever we ask a question to Ollama, it fills in this with the system prompt and it fills in our message into the prompt right here. The parameters here are the special tokens that Llama 3 requires. And then the system prompt is what we specified above. That just gets filled in right here. This format is very specific. So if you're going to go ahead and change this, I would suggest looking at the documentation I listed above. Here we append it, all these commands, and then we generate this model file here. So as you can see, this is how the model file looks. And we have it saved right here as well. And you can take a look at this just to ensure that it looks like this by going to your terminal, and you can just run cat model file. Yep, it's exactly what we wanted. And now we install Ollama. So it's a pretty simple one-line command right here. Just run curl. Awesome. And then to move forward, we have to make sure that we have an Ollama server running in the background. So in order to do this, it's pretty simple. We can simply clear this out and just run Ollama serve. So this is starting the Ollama server. Keep this in mind right here. We're going to be needing to use this a little bit later. So don't close this tab out here. And then it's a simple one-line create command. With this, we're going to actually create the Llama Brev Ollama model. So Might take a minute here. Awesome. So as you can see, our model has been built and now we can actually experiment it. So again, open up another tab. I can use this one right here. And I can go ahead and run Ollama run and then Llama Brev. And we named our model Llama Brev up here. So if you named it something else, go ahead and run that. So you could do Ollama run Llama dash Brev. So you can see the model is being loaded in. It's starting up. If I could say, who are you? As you can see, we've got an angry pirate stuck inside of a large language model. So we can keep on going here. He'd say, you sound like a pirate. Where are you? Oh, so the pirate knows that it's in this machine. So bonus points if you're able to get it to talk like a normal person. I can try once here. Are you really a pirate? Is that really your accent? So yeah, it really thinks it's a pirate right here. And the best part is if you want to try a different system prompt, if you want to make a coding assistant, for example, you can simply put here, you are a coding assistant that's extremely skilled in Python or Golang, and have it respond to you in that format right here. But now that we're done with this, let's now push this model to the Ollama registry. So the first thing you're going to do is actually sign up at ollama.ai/signup. So I already have an account. I'm Scooterman, and you can find my Llama Brev from earlier on when I did this right here. But yeah, what you're going to do is you're going to have to go into your settings. You're going to go to Ollama keys, and here you're going to have to add in the public key that was printed earlier. So if you go back to the notebook, go back to the Ollama serve tab. Up here, there's this SSH ED 25519. Go ahead and copy that, and then go ahead and paste it. Click add. And what this will let you do is this will authenticate your machine that's running the Jupyter Notebook to push models to the Ollama registry. So once you've done that, you can go back to the Jupyter Lab. And then you'll have to run this command right here, Ollama CP or Ollama copy, Llama Brev, username, and then model name. And then you're going to go ahead and push it. So we can go ahead and go to Ollama. We can go to models. Or we can go to my models, sorry. Let's do new. Let's do stuck pirate. Can you help poor pirate escape the infinite confines of an LLM? So we can go ahead and create this model, and this gives you the instructions on how to upload it. So in our case, we already have an existing model on our machine, so we can simply do this right here. So let's go ahead and go back to our Jupyter Notebook, and then we can run, let's exit this here. So we can do Control D, clear. Then we can run Ollama CP, llama-brev. Then we'll do Scooterman, that's me. We'll do stuck pirate. And again, this is Scooterman stuck pirate, comes from my username and then my new model that I've created on Ollama. We run this. It's now copied it. And then all we have to do is push it. So we could do Ollama push Scooterman / stuck pirate. So yeah, now it's starting the process of pushing the model to the Ollama registry. Awesome. So yeah, now as you can see, Ollama, our version of the model has been pushed, and we can go back to Ollama, and we just refresh this page here. Now we can see here's our model right here. There's the quantization, and since we just uploaded this, it's one tag, it's the latest tag. And here's our system prompt that we gave it as well. It was, you're a swashbuckling pirate stuck inside of a large language model. And yeah, so now the best part is, now that it's on the Ollama registry, you can now access this model from wherever that has Ollama installed. So I'm going to now close out my Jupyter Notebook. I'm going to go to my BrevDev console right here as well. I'm going to close out my Ollama notebook. Go ahead and click delete, so I'm not paying for it anymore. Awesome, it's been deleted. And now, if I go to my local computer right here, I can run Ollama pull Scooterman / stuck pirate. And this is actually going to pull my model from the Ollama registry itself. Okay, awesome. Seems like our model is done pulling. You can list the models that you have on your machine by using Ollama list. And as you can see, I've got a couple different models on my own computer. We're interested in this one right here, the Scooterman stuck pirate. So we can run, let's do clear. So we can run this model by doing Ollama run Scooterman - stuck pirate. And then we can say, what is the name of your pirate ship? Okay, so doesn't want to tell me the name of its ship. Let's say, who is your crew? So it's trying to plot the next move against the British Navy. Is the British Navy also stuck inside of LLM? Okay. Well, the pirate's not that happy with me, so we'll let the pirate go. But yeah, thank you guys so much for tuning in here. If you guys have any questions, I'll link our Discord and a way to get in contact with our team below. And please reach out to our team on our Discord if there's any specific content that you guys want to see, or if you guys want to see more Ollama content. And yeah, thank you so much, everyone.